Welcome to Wireless Future. I'm Emil Björnsson, and as always, I'm here in the podcast together with my colleague, Eric Larsson. How are you?
Oh, hi, Emil. Good. How are you?
I'm great. So I noticed that you a while ago gave a talk about rethinking wireless repeaters. So I thought that I will take this opportunity to talk with you about this topic and maybe to kick things off. So we have 5G out there and it seemed to be quite good. So what are the actual problem with cellular massive MIMO in 5G that you would like to improve?
Yeah, so that's a good question. I mean, so 5G, in fact, every wireless technology, I think, has been impressive for its time, and 5G in particular. Now, that said, we're still fighting with coverage holes. Covering the cell edge has always been difficult, and it will remain difficult. And on top of that, I mean, the probability that if you pick a user at random, it's actually located quite close to the cell edge is quite large. So we got the problem of covering the cell edge or coverage in general. We also got the problem of sending or providing multiple spatial streams to the same user, particularly in line of sight, of course. But unless there is enough scattering, then it's difficult to send more than a single or possibly two. I mean, if you've got polarization diversity, you could send two streams, but it's generally difficult to send more than one or two streams to a terminal, even though the terminal has multiple antennas. So those are challenges that remain. And there are, of course, ways that all this could be solved. The ultimate, I think, way to go for the future would be distributed MIMO, also known as cell-free MIMO or cell-free massive MIMO, where access points are spread out and cooperate phase coherently. Now, that's a huge challenge to build because of number one, backhaul, and number two, phase alignment that's needed for joint coherent transmission and downlink. And I think there is reasonable consensus, I would think, that DMIMO would ultimately be the way to go in order to build a wireless system that could offer ubiquitous coverage and uniform quality of service everywhere. It's essentially eliminating the problem with coverage holes. And on top of that, also be able to provide multi-stream transmission to users with multiple antennas. But it also seems that industry and both vendors and operators are reluctant because this is a big step to take. Deployment is a major issue. Again, backhaul and phase alignment are major technical problems that aren't really solved, at least not in a cost-effective way. So I think that's really where MIMO and 5G currently stands.
Right. So if I interpret this correctly, then it's like 5G is fast enough in terms of data speeds when you have good coverage, and also the capacity of an entire cell can be really good, at least if the users are in the middle of the cell, but then you have these coverage holes then or people who are standing on the wrong places and don't get fast speed. That sounds like a problem that you can really solve with this reconfigurable intelligent surfaces that there have been a lot of fuss about, don't you think?
Yeah, I mean, you could in principle. So just to be clear, I mean, we say cell edge, then a user at the cell edge might not necessarily be far away in terms of distance from the access point or from the base station, right? I mean, it could just be that it's in deep shadowing somewhere. It's in the basement or it's behind a building or something where it's just shadowed. But you're right. I mean, REES is an interesting technology that in principle could enhance the propagation environment by providing extra propagation paths that would improve coverage and improve the channel rank to enable multi-stream transmission, even to users with, even to a single mobile user with multiple antennas. Now, the challenge with REES, and I should also emphasize that pretty much everything that I say now and that I will say today applies to sub-10 gigahertz bands. Things are a little different once we move up to millimeter wave, not to mention terahertz. So I'll be sticking with arguments for the sub-10 gigahertz. I mean, really the most valuable frequencies, the lower bands below 10 gigahertz. And the challenge with RIS, I think, they are threefold. Number one, form factor. These gadgets are huge. So just finding a place to put them, to deploy them, would be a major challenge. Number two, control overhead. Because the atoms in the RIS would have to be reconfigured in real time, meaning that we need instantaneous channel state information to tune the load impedance or the phase shifts. And just getting their channel state information, I mean, is a challenge, and then controlling them using some presumably over-the-air control interface it's not technologically impossible necessarily to do, but it's very, very difficult. And to do this in a fast mobility environment, at some point you just hit the limit where it isn't possible to do. And the third, which is not as well known as it seems, challenge with RIS is that they aren't band selective. So that you deploy a RIS, and it will affect whatever spectrum piece that you own as operator. It will affect the propagation in that band, but it would also likewise affect the propagation in neighboring bands. And there are ways to make RIS at least slightly band selective, but then they become very complex and bulky and energy hungry, and it just doesn't seem to be technologically feasible to make them band selective enough that they only affect a specific frequency band that the specific operator happens to own. So these are major challenges with RIS, although they in principle, if deployed at scale and deployed appropriately, could enhance the propagation environment significantly. And now I recently learned that standardization of RIS in the 3GPP standardization body had been discontinued, presumably because of these reasons that I just mentioned. So I don't know if you agree, Emil, or if you have a different perspective on the issue.
I guess when it comes to RIS and standardization, probably the politically correct answer is that it has been postponed for the future.
Okay. So yeah, as I discontinued, probably it's been postponed.
Yeah, it might be brought up again if there is a demand. Yeah, no, I think there are. I mean, I've been surprised that how quickly people could actually do experiments and demonstrate that RIS works, but there are all these practical issues that they are describing if you want to do this in real world. And since you
that's
said
the thing. I mean, it's such a cool technology, no question, but there's a difference between building something in a lab and demonstrating that it's possible in some circumstances and actually deploying it at scale and in a commercially viable way.
Yeah, and since the licenses in these bands that we are talking about are extremely expensive, then you don't want someone to actively mess with your frequency band. And if you then deploy this RIS, and as you said, they are not band selective, and then you are very rapidly changing its configuration in order to fit users in your own band, then you will change the propagation conditions quite drastically also in other frequency bands, and that could create all kinds of things that would also then have to be standardized in order to avoid that this is bringing down your competing operators network.
Exactly.
All right, but then we have these coverage holes that you were describing, and part of this is also that when we are drawing a cellular network in a textbook or so, it's like there is some circular cells or hexagonal grid of things. But then in reality, maybe the base stations are not exactly on a hexagonal grid, but at least they are spread out in such a way, and there is an intended coverage area around them. But then there are all the buildings in between that makes the boundaries between the cells different, and there is hole inside the cells and all these kind of things. What I've noticed is that there are some places where you're really shadowed from the base station, such as in tunnels and so. And then the classical solution has been to deploy repeaters, which are placed outside the tunnel. They pick up a wide amount of spectrum there. It might be TV bands or radio, and then wireless bands and so on. There could be maybe multiple repeaters for different frequency ranges, and then they just leak the signal inside the tunnel. So that this seems to be a use case for repeater that is actually being used, and that is really a stupid repeater, because it's just amplifies whatever comes from the outside and leaks it inside the tunnel. But I've noticed recently that you have been doing research on something that is a little bit more of a smart repeater. You have papers like Achieving D-MIMO Performance with Repeater-Assisted Cellular MIMO and Stability Analysis of Interacting Wireless Repeaters and Reciprocity Calibration of Dual Antenna Repeaters. So then, what is your take there on using repeaters? There seem to be a new kind of smart repeaters coming out now.
Yeah, right. So that's right. So we gave a few papers that came out recently, and so the vision that we are exploring here is to build physically small, but smart repeaters that could be deployed at scale, and that would support reciprocity-based multi-user MIMO beamforming in TDD, so that these repeaters would be essentially acting as any other channel scatterer, but with an amplification. So think of them as like an active scatterer. You're totally right that repeaters as such have been used for a long time. Tunnels, for mostly for niche use cases. I mean, tunnels might be the most important one. So in that respect, the idea of using a repeater is not new in any sense. But I believe this vision of deploying swarms of reciprocal repeaters to support multi-user MIMO is rather fresh, and it also holds a lot of promise and potential. When you start to look at the performance you could actually get, it essentially becomes like you're enriching the propagation environment with more scatterers. And these scatterers not only scatter the signal, but they also amplify the signal. And you maintain reciprocity of propagation so that channel estimates at the base station learned from uplink pilots are valid also for the downlink.
All right, so you can use them in all the reciprocity-based beamforming solutions then.
Yeah, and the vision is also that the deployment by all means could be optimized, but in a way that this should work even with just a careless deployment. I mean, imagine that these devices could be made so physically small and so cheaply. You just buy them in bulk. And anywhere you got a power supply and you got like problem with coverage, or you got a desire to increase data rates and provide more propagation paths so that you can increase the rank of the channel, just install one. Just basically plug it into a wall socket and it configures itself through the network and just works without any centralized planning of where to raise the tower, build the towers, and where to install the access points and so forth. These guys, you just plug them in a wall socket and that's it. So it's like the ultimate vision, I think, that we have.
All right. So are there different kinds of such repeaters?
Yeah, absolutely. I mean, so repeaters come in many different forms, and the very simplest design is a single antenna repeater. So that's basically just like an antenna like this, and then it's connected to a microwave circulator, and then it makes a full duplex so that it can instantaneously receive a signal at the same time as it radiates that signal with amplification. These are the very simplest, and they are reciprocal inherently. Now, the difficulty with a single antenna repeater is very hard to build the hardware and get a gain of more than maybe 40 dB, order of magnitude 40 dB, which is not really enough to give this effect that we want to get with really improving coverage and rank and so on. The other kind of repeater is a dual antenna repeater. And I'm going to explain this now in the context of TDD operation, because to me that's the only really interesting case. I mean, where we naturally exploit reciprocity of propagation to get the CSI for multi-user MIMO beamforming. And with a dual antenna repeater, just like the name suggests, we got two antennas, and there are two amplification paths within the repeater. So one from antenna A to B, and one from antenna B to antenna A. Okay, and now, when the system operates on uplink, so we're in the uplink part of the slot, then the amplification path from A to B is activated. And when the system operates on downlink, the amplification path from B to A is activated. So there is a switch that decides which path from A to B or from B to A that's activated at a given point in time. And now, given that the gains and phases of these amplification paths can be made equal, then this repeater will appear in the propagation environment as a completely reciprocal, just like if it were a channel scatterer. It's like a passive scatterer, but with an active gain. Think of it that way. And in fact, the switch has to be there. Because if you think about it, I mean, so natural question to ask here would be, so why make this so complicated? Why don't you just, two antennas and then an amplifier path in between them? So I got a red and a blue here, A or B, whatever. Okay. So just an amplifier path in between them, you're done. No, that's not going to work. And the problem is that such a repeater would not be reciprocal. And the simplest way to, I guess, understand that is to think about like I'm sitting in the studio here in the basement, and supposedly I install this repeater with antenna A inside the basement, antenna B outside. Then I would get a really strong channel from the outside to the inside. But I would basically no channel gain from the inside to the outside. So can't be reciprocal. So a dual antenna repeater to work in TDD and to enable reciprocity, or to be reciprocal, would require this switching between a forward path and the reverse path. So I guess those are the basics. And for a dual antenna repeater, there's no really firm, to my understanding, upper limit on the gain that you could get. But in speed of hardware folks, they suggest that maybe 60 dB we definitely could get, maybe more, whether we need more. But I mean, if you just want like an order of magnitude ballpark number, then think maybe 60 dB.
Wow, so 60 dB, that's like a million time amplification then.
Yeah, 60, that's right, 60 dB. So we're talking, let's see, talking power here. 60 dB power, yeah.
Wow,
so
yeah.
That would be I mean, we're going to be careful with amplitude and power, but 60 dB power, yes.
And then compared to that single antenna repeater that you mentioned, then it's 100 times stronger.
Yeah, that would be 100 times. That's right, yeah.
As well. And then since there is this switch here, I guess you would have to tell the repeater if it is uplink or downlink that will be operating right now.
Absolutely. I mean, it would have to stay time synchronized with the TDD pattern, but that's an easy task because the switching, I mean, in TDD, the frame or the slot length might be, is it a millisecond or maybe half a millisecond or something of that sort. So you want to be within, a fraction of a millisecond here. But this is really a slow process, and they could be solved through some assistance through the network.
Surely
that would hardly be a difficulty. I mean,
right
in practice. Yeah.
But I guess this is one of the reasons why this kind of repeaters are now being standardized in 3GPP to be utilized in 5G, for example, and it's called network control repeaters because you need to be able to send this kind of control messages to tell it, should it be an uplink or downlink, and what is the frequency of change?
That's right. I mean, there has to be a control channel. That's why they're called network control or smart. I don't know the name smart because they don't really have that much intelligence, but they at least follow instructions from the network. And I think it's an important point to drive home one more time here that, granted, I mean, you need time synchronization on the order of a fraction of a millisecond or slightly less, I mean. But there's no need, in contrast to an access point for DMIMO, there is no need here for phase synchronization. And think about it like phase synchronization, where phase and time are equivalent. So phase synchronization, that means time synchronization within like a few picoseconds. Wow. Whereas we're talking about the fraction of a millisecond, which is a comparatively very easy game to play.
Exactly. So if you are like me, an academic person, you might not hear so much about repeaters because it's not something that we write much about in textbooks. But I think in the information theory area, there have been a long-standing analysis about relays. And there's a categorization of different types of relays and so on. So is there a core difference between repeaters and relays?
Yeah, that's a great point indeed. And it's also a big source of confusion, it seems. That So let's see if we can break this down. So a relay is a device that chops up the time axis into chunks, and then it receives a signal during some time window, okay, and then after the time window is over, it retransmits that signal. And they come in and they're done in different ways. The amplifying forward relays, they just take the waveform and amplify it and retransmit it. And we're talking about like the time window here might be a fraction of a millisecond or something. So it's quite large. I mean, it could be a whole frame or half a frame. So a TDD system would be like basically a frame. So those are called, so they could be done in just retransmitting a waveform. They would be amplifying forward relays. Or that relay could decode the data received during that window and then remodulate, recode it, and remodulate it and retransmit it. Those are called decode and forward relays. So those should not be conflated with repeaters, because a repeater instantaneously retransmits the signal. I mean, there's always be a delay, but for a repeater, we're talking about a few hundred nanoseconds at most as a delay. So that's like many thousands times less delay than, I mean, the block length or the window length in a relay. Now, to add to this confusion of terminology, repeaters are sometimes also called full duplex relays. Okay, so the whole terminology is a mess. And I don't know whether is repeater even a good word. Maybe not. But what should we call these gadgets? I mean, so in fact, we debated this a bit. Maybe we shouldn't call them repeaters. We should call them just active scatterers or path amplifiers or something. I don't know. I mean, but repeater at least is a word that's been around for a long time, and I think does have a well-defined meaning. Although there also seems to be a lot of confusion between relays and repeaters.
Right. Yeah, no, I think that is a good description. So let me relay the message then to the audience. So I guess then what you say, repeater would be what happens when you are talking in a microphone and there are loudspeakers in the room. Well, then it's immediately while you're speaking is just amplifying the message so everyone can hear it in the room. And then the amplify forward would be like you're saying one message, one sentence, and then right after you're done, it is sent out in the room. And the decoding forward is a little bit like someone is repeating your message, but with their own voice afterwards.
Yeah, that's a great analogy indeed.
Yeah, no, so this can be really confusing, but I think that there has been a little bit of a lack of mathematical analysis of these kind of repeaters that are just adding a little bit of extra delay to your propagation environment, but it's amplifying things a lot. Because this is a really powerful way of...
Absolutely. I mean, there's been very little academic, at least, research on how to use repeaters in networks. And you mentioned delay here. I think one point that ought to be made is that this delay is very small in comparison to pretty much everything else. I mean, particularly it's small compared to the cyclic prefix in an OFDM system, because I mean, essentially what happens here is that we add scatterers in the channel, will increase the excess delay or the delay spread of the channel. And now if the scatterers themselves introduce a small delay, we got to make sure that this delay is small in comparison to the cyclic prefix. But again, I mean, we're talking about hundreds of nanoseconds here to be compared with the cyclic prefix is hundreds of times longer, so it's totally negligible.
Right. And I think when people are analyzing also these kind of classical relays that are operating in two phases, first receive and then retransmit, then in those cases, since you lose half of your time resources because you need to listen before you repeat it, there is always some kind of trade-off there between should you really use this, or is it better to just use all the time and transmit directly to the receiver with a weaker signal. But for the repeaters, there's really nothing to lose here, I guess.
That's a good point. I mean, for relays, there's this loss. Information theorists, I think, like to call this a pre-log factor. So basically, you go from log 2 of 1 plus signal to noise ratio to 1/2 of log 2 of 1 plus signal to noise ratio. So that loss, I mean, the idea is that for a relay to be useful, it has to really provide so much benefit that we can by far well compensate for that 1/2 factor that multiplies the spectral efficiency.
And then going back to the RIS, the reconfigurable intelligent surfaces, isn't this also some kind of repeater? The signal comes into it and it's with a very short delay reflects the signal in some particular direction. Can one compare these things somehow?
Yeah, in a way, I think. I mean, a RIS could do the job of a repeater, put it that way. It's just that it's going to be so much larger and bulkier, and you definitely can compare them. I think a useful way of understanding how they relate in terms of amplification gain is to... So this is going to be like a very rough first order argument, but think about it this way, that if we were to compare a repeater whose effective antenna area were the same as the area of a patch, one of the atoms in the RIS. Okay, so that would be essentially something like half a wavelength by half a wavelength in size. Then the repeater will offer a gain, an amplification of power, which is, let's say, A. A is an alpha. That is the gain. And the RIS, well, the atoms themselves, they will not amplify the signal. They will just scatter the signal, right? But if you think about the RIS and it's got like M as mic atoms, then the aperture of the RIS will be proportional to M, to mic. Okay, that means that the power received by the RIS will scale proportionally to M. And now what the RIS essentially does is that it air quotes retransmits the wave. It beamforms the wave as if the RIS were a MIMO array with M antennas. Yeah, and while doing that, it will achieve an array gain or a beamforming gain also of M as in mic. So the gain of the RIS would be mic squared. So to make them equal, the repeater and the RIS, then the repeater gain, the A, would be the M squared. So to achieve a, let's say, 60 dB gain with the RIS, you would need 60 dB is a millions, you would need a mic would have to be 1,000, so you would need 1,000 atoms. I mean, this is just an order of magnitude argument to appreciate the kind of rough relation between the amplification gain of a repeater versus the gain that the RIS would offer.
All right, yeah. So I guess both a RIS and a repeater will need a power supply. For the RIS, it's maybe in particular to be able to be controlled, but also to somehow to keep its configuration static or what you want it to be. And for the repeater, you also need to control it, but then you need to amplify the signal. But it's really like it consumes perhaps more power, but it's much smaller than the RIS as well.
Yeah, so I mean, two things here. One, you said that it keeps it static. I think on the contrary, the RIS will have to reconfigure itself every time the channel impulse responses change, right? Which means every channel coherence time interval or something of that sort. Whereas the repeater will not reconfigure itself at all. It will just stay there and function as a linear time invariant system, literally time invariant. I mean, so do the same thing. Its impulse response is not going to change over time. Power, in terms of power consumption, that is something I want to be very careful in really expressing any statements or opinions about. My gut feeling is that, I mean, a repeater obviously could be made a lot smaller in terms of physical form factor. Whether it could be made more like energy efficient or draw less power, I'm not totally sure. I think a RIS, since a RIS doesn't have amplifiers or much of active circuitry, it could potentially be built, implemented with very low power consumption, maybe with less power consumption than the repeater. Is very possible.
Right.
I don't even know whether there are truly optimized designs here. And one challenge is that, well, in the repeater, it's basically a piece of analog hardware with a little bit of control logic. It's very simple. The RIS doesn't have any amplifiers or any analog electronics, really, but it has a lot of control logic that needs to be operating at a high speed to tune it and all of that. So I don't even know if there are optimized implementations of RIS or repeaters that could be meaningfully compared, because it's one thing to build something in the lab and demonstrate that it's actually possible to tune a RIS or it's possible to build this sort of repeater. It's a different thing to build them on a production line with optimized hardware and like maximized energy efficiency. So that one I don't really know, honestly.
Yeah, no, I totally agree that trying to compare the power consumption is a bit speculative at this stage. Probably also the power consumption of whatever solution you choose will be very small compared to the power consumption of a macro base station. So you could have many of them in a macro base station cell without it being an important part. I can just clarify that what I meant with the static configuration risk was that every time you change the configuration, then you have all of these atoms which contains diodes which need to either stay in a few different discrete number of sets, or you have a bias voltage over a circuit, and whatever implementation you have, there is some kind of power dissipations in keeping the configuration constant for that period of time you want it to be constant. So there is some power consumption there, even if you are not adding the power to the wireless signal.
Oh, I see. That's good to know. Yeah.
So I think in the beginning you were mentioning then that the problem with cellular massive MIMO is, okay, you have your tall base stations and you have a particular cell range, and then there are all kinds of objects that might create shadowing, and then you have this coverage hole here and there, and then you describe to distribute the antennas in this distributed MIMO setting as the ideal way of solving the problem, but it might not be economically feasible, at least not in the short term, and there might be all these technical issues that you were alluding to as well. So if we then take our cellular massive MIMO bases that we have today and throw in these network control repeaters and operate them in a good way, what kind of performance can we get? Would it be something similar to distributed MIMO?
Yeah, I mean, I think it remains to perform really detailed system simulation and analysis here. But so in one of the papers you mentioned that we had published, we got some elementary simulations, and there we compared, I think, cellular MIMO to distributed MIMO to small cells, which of course doesn't work very well because of interference, as we know. And repeater-resistant MIMO doesn't bring us to D-MIMO performance. No, it doesn't. But it does improve quite a bit over the cellular, which I think is a promising conclusion that definitely warrants more and deeper. I mean, I should also say that there's also a lot of opportunity to optimize things here that I believe are mostly open questions. I mean, both in terms of how to optimize gains, for example, of the repeaters, and how often do we need to reconfigure these gains depending on traffic load and where the users are and so on, and what performance do we eventually get. So I would even go that far to state that there might be more open questions than solved questions in this domain right now. Yes.
Right. And then a little bit in comparison then to RIS as well. So there we had this issue that it's not really band selective, but I guess you can have some filters in or you need to have it in the repeaters in order to filter out certain bands, or
you would want filters, and there are different hardware architectures in terms of how these filters will be implemented. I mean, they could be done at passband, or the signal could be down converted and then filtered. The exact trade-offs there, I think, are largely unexplored in terms of, because again there's this trade-off between cost and implementation complexity and energy consumption and sharpness of these filters, and you probably want these filters to be pretty sharp, and then there's also a trade-off between the sharper you make a filter, the longer will its impulse response be, obviously, and that means introducing a delay. Keep the filter causal, I mean it will introduce a delay. Now this delay is still very, very small. I mean, compared to the OFDM cyclic prefix, it's hardly an issue. But there could be other things like, so one is that a repeater that does filtering in the passband, it doesn't have a mixer, so there's no phase noise. Okay, but the repeater that does have that does down convert the signal before the filtering, it would need a mixer, so there would be phase noise. Now, there would be the same phase noise affecting the receive branch as the transmit branch. So that phase noise would cancel, but not completely, because there is a delay in between of the down conversion and the up conversion. And those are, I think, in a way more electronics challenges to sort out, but we should definitely be aware, I mean, of the phenomena here and the possible trade-offs that would need to be considered.
Right, also this issue, how a RIS could change the channel of other operators in a quick manner, because you change the configuration quite quickly. I think one of the selling points you have here for a dual antenna repeater is also that you don't have to change its configuration very often. You turn it on, and then even if you happen to amplify the signals in a neighboring frequency band, that might even be a good thing for another operator as well.
Oh, it might not necessarily be bad, but I mean, this is all host of regulatory issues. What happens if you start to transmit in a band that somebody else owns, right. And so on. So that one, I honestly, I don't really know. But you're right. I mean, so one of the selling points of this vision of deploying swarms of smart repeaters is that, granted, they are configurable, so their gains can be configured, but that gain should change very slowly over time. So basically only reconfigure them where something has changed in the network, some new user appears somewhere and needs service, or, I mean, on a fairly slow time scale.
Yeah, I think the important thing is to not change things drastically within one resource block or things like that, because I think when we now use TDD systems, the operators using neighboring frequency bands, they need to synchronize already their uplink and downlink to not create strange interference effects. And then, the repeaters will then also be matched to the same kind of switching between uplink and downlink. And as long as you inside each of these bands are not changing things, so it's static in the beginning, when you start your channel estimation, you will at least estimate the channel including the repeater, and you will not mess it up afterwards.
Right. Yeah, that's a good point. I mean, so
you mentioned these numbers with 40 dB or 60 dB power amplification. What if we could build it even stronger? Would there be like problems arising if you amplify things enormously strongly?
Yeah, at some point there might be. I mean, so the thing is here that these repeaters will eventually interact with each other, so that the signal transmitted by one repeater will be picked up by a nearby repeater and amplified, and then picked up, that amplified signal again being picked up by the first repeater and so on, creating like a positive feedback loop. It's a little bit like if you stand in a room and you speak with a microphone that's connected to a loudspeaker, and then you move the mic too close to the loudspeaker, then you'll hear this like hissing sound of when that feedback loop is created. I don't think I can demo this here, but in principle, I mean, the effect would be if I took my earphone here and I move it closer and closer to the mic. This mic is pretty sensitive, by the way. I don't know if I dare to do it, what actually would happen here, but at some point the mic would pick up the sound from the earphone and create this positive feedback loop. And the same thing will happen with these repeaters, if they are too close to each other or if the gain is too high. So there is a stability issue here that is like a totally new phenomenon on the wireless physical layer that will have to be dealt with. I mean, basically making sure that, well, I said earlier, we could deploy repeaters just carelessly, just connect them wherever you like. I mean, so that means you would have to make sure that the gain is not set too high if they are too close to each other. And that turned out to be a little bit of an interesting mathematical like problem to analyze, indeed. Yeah.
Right, that's interesting. Also, the analogy there with the microphone and the loudspeaker connected to each other, and I guess even if you don't get the feedback loop where the signal just becomes stronger and stronger and stronger, which is what you can feel in those situations with the microphone and loudspeaker. I guess if they start to send the signal back and forth to each other, even if it is sort of decaying, you create then a much longer delay spread of your channel.
That is true. So yeah, that's totally true. I mean, in fact, if you think about the simplest instance would be that you got two repeaters that interact, and then you can work in closed form the impulse response of that feedback system. And as the way it comes out is a sequence of direct deltas that go like down. But the amplitude, given that we're within the stability limit, the amplitudes of these weights of these direct deltas go exponentially fast to zero. So to me, it seems that, well, as long as we are within significant margin from the stability limit, then we don't need to worry about the increase in dispersion. But we're totally right that this qualitatively that effect is there. Yeah.
What about noise then? You amplify the noise, or is there noise to amplify?
Yeah, that's a good point. And that's another thing here that's non-obvious with repeaters, that now these guys will be active noise sources. And think about just a repeater that's too far away from anything to pick up a useful signal, but then you crank up the gain very high. So what will happen is that this repeater will just start to radiate noise and then harm performance rather than improve performance in the network. So that's another totally new phenomenon on the wireless physical layer that, to my knowledge, has not been considered before. I mean, so this is another funny thing here is that now I believe this concept has a lot of potential. Compared to REES, it has great potential. But also, it opens a number of totally new research directions on the physical layer or for wireless physical layer research, which is, I think, fun in itself and dearly needed, by the way, for the community. So.
Right. When I read up a little bit about what kind of functionalities that they are standardizing when it comes to these network control repeaters, I mean, one of the basic things is just an on-off command. So you can turn off a repeater when it's only radiating noise.
Yeah, sure. I mean, but I think, control messages here might include like setting the gain, obviously, and then some functionality for alignment to the TDD pattern. You also want functionality for calibration, so that to make the forward and the reverse path equal in a dual antenna repeater, to make them reciprocal. So in fact, if you think about like what would be the requirements that we would have to impose on a smart repeater like this that could be deployed at scale in the swarm? Well, you want them to be reciprocal. That's the number one thing, which might require, or probably will require, calibration of some sort, so that there will have to be a tunable phase shift or even amplitude gain scaling inside, so that to make the forward and reverse path equal, and some way of measuring, like to calibrate using external signals, which, by the way, we had in one of the papers, I think. And the number two is this alignment with the TDD pattern. The third is the band selectivity. The fourth is the delay should be very small, which it will be, I mean, by all means. We would also need requirements on linearity, because now we got devices here with active power amplifiers, and power amplifiers are never perfectly linear. And whenever you got an amplifier, you got out of band radiation as a challenge, and ACLR, and that I think is largely a matter of deciding in the standard how much of out of band radiation can we tolerate, and then the hardware and the amplifiers will have to be accordingly designed, and the back-off operating point and so forth has to be selected accordingly.
When you mentioned this possibility of two different repeaters to start sending signals back and forth to each other and amplifying, within one dual antenna repeater, will there also be some kind of loopback interference between the transmit and receive antenna?
Yeah, absolutely. I mean, there'll be designing these gadgets the hardware itself is a real challenge. But that's in a way always been there in the designing anything that operates full duplex. This is a major challenge to build the electronics. The new thing here is that we got like different repeaters that could start interacting with one another over the actual propagation channel.
Right. So when people have been analyzing where to deploy RIS, of course, your propagation environment would determine where you can feasibly deploy them. But since you have this kind of dual path loss, the path loss from the transmitter to the RIS and from the RIS to the receiver is multiplied with shudder, it turns out that you typically want to put the RIS somewhere in the middle between the transmitter and the receiver. But since you add noise in these kind of repeaters, does that change where the ideal repeater locations are?
Yeah, that's a good question. What would be the optimal place to put the repeater? So first, I think actually for the RIS, the optimal location is not in the middle. It's rather close to either the transmitter or to the receiver.
Right, yeah. Sorry, you're right. Yeah. Yes.
But it seems to be a very common misconception out there that a lot of people seem to believe that the optimal location of the RIS is in the middle. I guess because a lot of papers have illustrations where you get like mobile terminal, you got a base station, and you got the RIS somewhere like located in between of them. But if you just look from a path loss perspective, because the overall path loss via the RIS is the product of path loss from the mobile terminal to the RIS, and then multiplied by the path loss from the RIS to the base station, then the optimal location would be to be either close to the transmitter or either close to the transmitter or close to the receiver. The same would apply for a repeater, but with the important distinction that with the repeater we also have a power constraint on the emitted power. And if you think about it, if you were to put so here's the base station transmitting, and you put the repeater very close, you pick up the whole signal without much of any path loss, and amplified 60 dB, then that's impossible. So you can also consider the power constraint of the repeater itself, and then the optimal point will not be to put it close to the transmitter. So there's a difference there in terms of how this plays out for a RIS versus a repeater.
Okay, I was thinking that since the noise is added in the repeater, then the signal to noise ratio that you have for the received signal to the repeater would sort of be what is maintained after you have amplified it as well. So that for that perspective, you don't want the repeater to be very close to the receiver, but rather closer to the transmitter, so the signal is stronger there.
Sure. I mean, you're right. You got the noise, but so my basic point was that if you put it too close to the transmitter, you could not allow it to operate with its maximum permissible gain. And but again, I mean, I think deployment. This is an open problem that's, to my knowledge, not been analyzed. If we were to deploy repeaters of this sort, so reciprocal, smart network-controlled repeaters in big, at scale, in swarms, in a cell, where is the best place to put them? Now, in a way, this goes somewhat against the main selling argument of repeaters, which is that you could just deploy them carelessly. Anywhere you get the power supply, you put one. But I think it would still be interesting to know what would the optimal deployment actually look like. So that's another new problem uncovered here for wireless research, indeed. Yes.
So what performance gains do you expect in a real system then?
I mean, we will never get DMIMO performance, because DMIMO in my world is like the ultimate solution for wireless access. But we'll be getting somewhere in between of standard cellular massive MIMO and what you could get with DMIMO. DMIMO here being every base station phase coherently cooperating with every one else. And I think I'll have to pass on the question. I mean, I'm an agnostic here. To me, this swarm repeater concept has a lot of potential. And on top of that, it's also a good research problem, because it opens totally new research directions and problems and questions that just haven't been asked before. In a real system, what performance we can get, I think, remains open.
Right. But you do have some simulation result in this paper achieving DMIMO performance with repeater-assisted cellular MIMO.
I mean, in the paper, there was one of the papers here you mentioned was some simulation results, and I mean, we're getting there. We're not getting exactly to the DMIMO, but we're getting we're getting closer to DMIMO than to the cellular MIMO in any case, and way better than the small cell than a small cell solution. I mean, small cell would be to, rather than putting repeaters, you put a small cell there that will just interfere with everybody else and create a whole mess. That's what really happens.
But isn't a repeater in a way also a base station with a like wireless backhaul? The signals.
Yeah, I mean that's actually a nice way of phrasing it. I was thinking about it, that it's like the simplest possible way of building a base station would be something that takes in the backhaul and radiates that backhaul instantaneously. You could think of it like that, maybe.
Yeah, and I think from that perspective, this decode and forward relay that we mentioned earlier that is using two phases, that is like also a small base station with an integrated access and backhaul kind of technology where the backhaul is to send the signal to that repeater and then the transmission is like that.
I mean, why not? You could think of it like that, I guess. Yeah.
No, I think 3DPP is using some of those terminologies when they are now discussing this network control repeaters as well. Another thing that they are talking about is particular use of repeaters in millimeter wave frequencies in addition.
Millimeter wave, yeah.
So I think a lot of what you described is this vision about improving coverage at the lower frequency bands, which is where we are using things today.
Well, I mean, a lot of the discussion we had here was centered, or at least my mindset is and has been sub 10 gigahertz. Some things might change if we move, or even sub 6 gigahertz, let's say. Some things might change if we move up to millimeter wave bands, like around 30 gigahertz. I mean, one thing that does change is the argument with form factor for a RIS, for example, that at millimeter wave, RIS could be the atoms are smaller. So it doesn't change really the comparison arguments that we made, but it might change some of the arguments about difficulties of deployment and so on. I haven't thought so much about it for millimeter wave, to be honest. I tend to focus most of my thinking on the low frequency bands where the real valuable spectrum is located.
Yeah, no, definitely. So as long as we have enough capacity in those bands, that seems to be the logical thing to continue and just improving those bands.
Yeah, and we do. I mean, with massive spatial multiplexing, we will. So.
But I think when they have been trying to deploy millimeter wave networks, then coverage holes in between the cells have been one of the issues. So I think from that perspective, if one wants to roll out large-scale deployments of millimeter wave technology in the future, then these repeaters might also be the way of sort of covering the holes in between. So I think.
But that's a great point, indeed. I mean, so you're saying that the cellage or the coverage problem more generally is a bigger deal at millimeter wave. Even it might, I mean, it's a big deal in some way, or it's a difficulty at least in lower bands, but it might be a much bigger deal even at millimeter wave bands, and therefore the need for something like repeaters or RIS or possibly something else would be higher there.
No, and in those situations, since antennas normally become smaller, then we usually compensate by having arrays of antennas, and then one could potentially have this kind of network control repeaters with small analog beamforming arrays, both for the transmitter side and for the receiver side, and do whatever you described there with the dual antenna case, but there will be two different phased arrays that are operating instead. And I think the standardization then in 3DPP is also describing how you can then tell the repeater what beam direction to receive from and what beam direction to transmit in. But of course, then you start adding some of these complications that you would have with the RIS as well.
So then,
so maybe the comparison between RIS and with these smart or network control repeaters will be, it would be more of a competition in millimeter wave frequencies between technologies than at the lower frequencies that we talked about.
That I absolutely agree. That's a great point, Emil, indeed. And I mean, but I think to reiterate that point, that the vision that we have put forth in these papers that you mentioned is really that these repeaters should be small and very simple. So it means no beamforming or anything of that sort. Now, if you go beamforming, which you might want to do at millimeter wave, and you're right, I mean, the form factor is not an issue any longer, then the question is also what is a repeater versus what is an... I've seen architectures with like an array on one side and an array on the other side, and then some phase shifters and an amplifier in the middle, and people call that, I think people call that Reese. No, it's not really Reese. It's more, to me, it's more repeater. So right. Where do we draw? The boundary becomes blurred in a way.
Yeah. No, and
also
there's also the name active Reese, which...
yeah, there's this whole field of active Reese, and I mean, now what is a repeater versus an active Reese and so forth. So I think the context here, which I want to say one more time, the context of the papers you mentioned, about the discussion we had, is now this at low frequency bands, building these very simple repeaters that don't have like active any beamforming or anything of that sort built in. Yeah.
So if we should try to wrap things up here, do you think this is the future, that we will sort of 5G will evolve by keeping the base stations roughly as we have today and then fill in with some repeaters in order to provide this kind of ubiquitous coverage for all the kinds of cool services that people have been imagining?
That's a good question. I mean, I think the honest answer is I don't know. I'm agnostic, but I do think this concept has a lot of potential that warrants a careful look, really. I mean, both to solve like individual technical challenges that we talked about with stability and reciprocity, calibration, hardware design, power control, configuration of gains. I think we probably covered most, if not all, of those challenges here. So definitely this concept warrants a detailed study of solving those individual technical challenges, but also of really performing serious comparisons in a system context between well, what are the comparison points? I mean, Reese is the obvious technology to compare with, I think. Small cells, we know, doesn't quite work because it has great interference, but DMIMO definitely, and maybe some forms of DMIMO, that simpler forms of DMIMO that would be like simpler to build and deploy, could be another good baseline for comparison. So I think that would be my answer here too. I mean, a very pertinent question of yours indeed.
All right, that's very interesting. So, yeah, I think the standards now that starts to include this kind of things start to be called 5G advanced. So let's see what kind of advancement we will actually see out there in reality.
Yeah, we will indeed, yes.
Right.
Yeah.
So it has been great talking to you. I learned a lot about these network controlled repeaters, and I hope that the audience have also done that, and we will put links to the papers where you can read more about this topic in the description of this episode. So thank you.
Thank you.